World Spaceflight News Special Report. This excerpt from the WSN SpaceNewscast reports on NASA's selection of 13 regions on the south pole of the Moon for the Artemis III lunar landing mission.
In the run-up to the Artemis launch, NASA has unveiled the first round of candidate lunar landing locations for the Artemis III mission, planned for no earlier than late 2025. The 13 regions are each 15 by 15 kilometers, or about 10 by 10 miles. Within each region, there are 10 or more pinpoint landing sites, marking 100-meter ellipses. The small site target is designed to allow easy access to favorable work locations. All the regions are located within 6 degrees of the South Pole, called a target-rich environment by scientists. Officials at the media teleconference, an audio-only event, noted that NASA is seeking input from the international lunar science community to narrow down the site selection, which should come about 18 months prior to launch. Here is a rundown of the site locations.
But the 13 regions that we're looking at are the rim of Amundsen crater, the northeastern rim of the Nobile crater. On the image, we call that Nobile 2. The western rim of Nobile crater, we call that Nobile 1 on the image. The Leibniz Beta Plateau, the rim of Faustini crater. There's an elevated region between the Shackleton crater and the Slater crater. The Malapert Massif. There are 2 locations along a high-standing ridge, and that ridge connects the Shackleton and the Degerlosh craters. There's a location on the rim of Hallworth crater. There are 2 locations along the rim of Degerlosh crater itself, and there's a massif between the Degerlosh crater and the Kocher craters.
Together, the regions provide landing options for all potential Artemis III launch opportunities. Specific landing sites are tightly coupled to the timing of the launch window, so multiple regions ensure flexibility to launch throughout the year. To select the regions, an agency-wide team of scientists and engineers assessed the area near the lunar South Pole using data from NASA's Lunar Reconnaissance Orbiter and decades of publications and lunar science findings. LRO is not currently in orbit that will enable any further imaging of these sites, however. In addition to considering launch window availability, the team evaluated regions based on their ability to accommodate a safe landing, using criteria including terrain slope, ease of communications with Earth, and lighting conditions. To determine accessibility, the team also considered combined capabilities of the Space Launch System rocket, the Orion spacecraft, and the SpaceX-provided Starship human landing system. All regions considered are scientifically significant because of their proximity to the lunar South Pole, which is an area that contains permanently shadowed regions rich in resources and in terrain unexplored by humans. Quote, several of the proposed sites within the regions are located among some of the oldest parts of the Moon, and together with the permanently shadowed regions, provide the opportunity to learn about the history of the Moon through previously unstudied lunar materials, said Sarah Noble, Artemis lunar science lead for NASA's Planetary Science Division. The analysis team weighed other landing criteria with specific Artemis III science objectives, including the goal to land close enough to a permanently shadowed region to allow crew to conduct a moonwalk while limiting disturbance when landing. This will allow the crew to collect samples and conduct scientific analysis in an uncompromised area, yielding important information about the depth, distribution, and composition of water ice that was confirmed at the Moon's south pole. The team identified regions that can fulfill the moonwalk objective by ensuring proximity to permanently shadowed regions and also factored in other lighting conditions. All 13 regions contain sites that provide continuous access to sunlight throughout a 6.5-day period, the planned duration of the Artemis III surface mission. Access to sunlight is critical for a long-term stay at the moon because it provides a power source and minimizes temperature variations. Quote, developing a blueprint for exploring the solar systems means learning how to use resources that are available to us while also preserving their scientific integrity, unquote, said Jacob Bleacher, Chief Exploration Scientist for NASA. Lunar water ice is valuable from a scientific perspective and also as a resource because from it we can extract oxygen and hydrogen for life support systems and fuel. The issue of the composition of the first landing crew was raised at the teleconference. When the Artemis program was first announced by Administrator Bridenstine, it was stated that the landing would feature the first woman on the moon. Later, the Biden administration added that it would include the first person of color. Now, Mark Kirasich, Deputy Associate Administrator for the Artemis Campaign Development Division, has raised some doubt about the second goal.
We know on the first mission we are going to land a woman, and whether or not that woman will be a person of color or either of the two crew members will be a person of color, that's not a mandatory requirement for the first mission. Could happen. It could be one of the subsequent missions.
There were no representatives from SpaceX, the contractor for the Starship-derived human landing system, at the conference. Questions about the capabilities and limitations of the lander were referred to the company, which has revealed little about the status of its design. On several occasions, it was noted that the design is incomplete and issues are still being resolved. The lander will have some manual controls, and the landing site selection for the SpaceX uncrewed demo flight, now penciled in for 2024, is the responsibility of the company, not NASA. It does have to be within 6 degrees of the South Pole, but there is no requirement that it be at any of the 13 candidate regions. The official said that Starship may also carry non-NASA cargo or commercial experiments on the Artemis mission, and they would not provide information on the disposition of the lander after it returns the landing crew to Orion in lunar orbit.
I think most space enthusiasts are familiar with Apollo views of the moon. Astronauts and rovers exploring fantastic features of the moon, features that are all bathed in sunlight as far as the eye can see. However, at the poles, the lunar seasons, coupled with an extremely low axial tilt for the moon of about 1 to 1.5 degrees, they yield a much different scene. At the equator, a lunar day spans roughly 14 Earth days of continuous sunlight, followed by about 14 Earth days of continuous darkness. That's in the order of 330, 340 hours of sunlight and darkness, repeated over and over. Nearly every place near the equator has a 50-50 split of light and darkness. During the daytime at the equator, you're completely in sunlight. You move a mile over there, 5 miles back here, you remain in sunlight. At the poles, the lighting is different. The ratio of light to darkness can vary significantly. It ranges from permanent darkness, locations that never see sunlight, to nearly complete exposure to the sun through a lunar year. What makes this situation even more complicated is that the ratio of light to darkness at any location, well, it varies over short distances. In as little as a few miles, sometimes even short distances like a football field, that ratio can be drastically different. While these sunlight conditions might sound complicated, thanks to LRO and our other spacecraft at the moon, these conditions are predictable. Although some locations might be dark most of the year, we will know when they are going to be in the light. While it might seem complicated, it's these very conditions that provide us with the rationale for going to the South Pole. Finding locations with greater than average amounts of light enable us to design systems that take advantage of light for energy and thermal control. Similarly, locations in permanent shadow, which are unique to the poles, provide opportunities for access to water and other volatiles that are trapped there, but they don't become stripped away by the solar wind. Although these conditions can be modeled and predicted, I think you can imagine many different technical considerations must be made in order to land here. Knowing that Apollo 17 would be the last Apollo mission to the moon, Apollo 17 astronaut Eugene Cernan reflected on his expectations. At that time he stated, The theme of our mission is that this isn't the end. We've just begun to crawl with the Apollo program. We're just now hoping that we can begin to walk as we press on into the future. Well, sir, we accept the challenge. Skylab, Shuttle, the International Space Station, they have all taught us how to survive and thrive in low Earth orbit. And we're now ready to take that walk. Discussing the regions where Artemis III mission can land is our exciting first step on that path. We have to learn how to operate in some of these locations that are unique, of which, as you note, the permanently shadowed locations, they are certainly a unique aspect to the polar region. One of the things, I think Sarah noted this already, and I did earlier as well, these permanently shadowed locations may contain volatiles, frozen volatiles, in fact, that maybe we can go sample and begin to learn about. So we have a lot of questions about these permanently shadowed locations. What is the makeup, what is the relationship of volatiles and the regolith? What is the surface roughness inside these craters? Can we get down to the volatiles? Is there enough volatile there that we can actually sample it and or potentially extract larger volumes of it in the future? These are all questions we have. So the skill sets needed to do that will most likely fundamentally be, from a science perspective, understanding the geoscience aspects to it. So kind of your traditional field science skills we'll need to use there. But we're also going to have to learn how to operate in that total darkness on the lunar surface. So we do have questions about how much reflected light might go into these locations, and how do we actually navigate and work inside there, and actually how cold do they get at the scale of a person walking around. These are all questions we have. So permanently shadowed locations, regions, will certainly be a target of interest for us, trying to just understand them, understand what they hold for us from a science perspective and from a resource perspective, and in general, just starting to learn how to operate in there. So that's kind of what we're going to have to bring forward.
Yeah, and I can add to that, Jake, that it's not just operating in these permanently shadowed regions, but understanding how to do field geology in these extreme lighting conditions, even outside of these permanently shadowed craters, is going to be a challenge. And so we're actually practicing. We're, going out at night and doing analog activities where we bring our own sun and we test out the lights on the suits and make sure that our astronauts can actually see the geology that they're trying to study. And so we are actually already in practicing that and trying to learn how to do that and to optimize the situation for the astronauts when they get there.
Leo Enright, a veteran space reporter from Irish television, asked about the challenge posed by ever-changing lighting conditions at the sites. Here was the response.
Yeah, I'm still a little bit, I'm trying to get my head around these moving opportunities, because if you spool the image that shows us the 13 candidate landing regions is one instant in a 2-week cycle. And if you spool around with that video, only 2 of these sites are visible at any time. They all, they disappear into darkness constantly. So you're talking here about target regions, each one of which only has, it would seem, 4 or 5 days at most where they're fully lit. I mean, you're really trying to thread a needle here, and I'm trying to understand how you do that and keep an astronaut crew safe.
So this is Jake. I can start to answer that question. You are characterizing exactly the challenge that we're dealing with right now. And, as I mentioned in my opening, the Apollo missions took full advantage of the lighting conditions near the equator, knowing that they would have the equivalent of 14 continuous Earth days of light once per month. So they could land in those locations and know that they would have a stretch of 9-10 days of light. But you touched on exactly the difference with the South Polar region. Any of these locations is not in light all the time, neither were the equatorial regions. So we have to model and understand exactly when they do enter into light and for how long. And so one of the conditions we're looking at is that it would need to be in light for Artemis III throughout the duration of the mission. As Mark talked about, it's between 6 and 7 day long mission. So we need that stretch of sunlight, but that's really all we need. So it could be in darkness much of the rest of the time, but if it comes into light for that period of time at the right launch opportunity, we could go there. That's why we're looking at a number of sites, not narrowed down to a specific single one at this point. We have 13 regions, each of which include multiple sites. And as you said, we're trying to look at how we thread that needle. And then, as Mark said, how can we try to reduce that number from 13 down to a smaller number by better understanding with our modeling and also working with SpaceX to bring them into that conversation as well.
The issue of lighting conditions has figured prominently in planning. A presentation at the 2020 Lunar Science Workshop was entitled, quote, "Blinded by the Light, Illumination Considerations for the Artemis Site Selection, Traverse Planning, and Instrument Operations." The authors from NASA and supporting institutions said that the South Pole has, quote, "some of the harshest illumination conditions in the solar system," a rather daunting situation. They noted that the sun will always be within a few degrees of the horizon. The experience of Apollo astronauts was analyzed. It was determined that the expected sun position will reduce the crew's ability to see terrain details and slow mobility. Quote, "While we are not proposing that traverses only operate in the cross-sun direction, it will likely reduce wear and tear on the crew and the possibility of rover damage if time traveling towards or away from the sun is minimized. Apollo 17 utilized a tacking approach, minimizing the amount of time pointed up sun. Apollo crews utilized visors and sunshades on their helmets or a gloved hand to block the sun. However, in the case of Artemis, the sun may be much closer to the horizon, making such mitigations challenging. The use of opaque visors may improve up-sun viewing, at the cost of visibility of the surface and when viewing across sun."